Hey Remington, we are on the last section of the chapter, so tomorrow we'll start chapter review for chapter 3. But this is perpendiculars and distance, okay? So, we're not going to write anything down on our yellow sheets today. We have this diagram right here. Do you guys see him? Whoop. We're going to talk about this. Here is the wall. Okay, let's say that guy is the wall, like this wall that has a whiteboard, okay? And let's say here's me, or you, or whoever, right? And I want to measure the distance that I am or you are to the wall, right? Okay, so we could measure like this distance here. We could measure this distance, this distance, this distance. We could measure all along the wall, like how far you are to the wall, okay? Just so you're clear, if I'm standing right here to the wall, I can measure from here to the wall there. I can measure here to the wall there. I can measure here to the wall, here to the wall, here to the corner. You know, I can do any of those measurements. Which one do you go off of? If I say, how far are you to the wall?
Close.
Which one on there do you go off of? The closest one. Yes, the closest one. No, you're right. You're right. The closest one. Which one is the closest one? C to D. This is going to be the best, most accurate representation of the distance, right? Because it is what in relationship to the wall? Perpendicular. I like that word. Perpendicular. Okay. So this CD is making a T with the wall. Okay. I would not measure at any other angle. Like this isn't going to tell me anything, or this isn't going to tell me anything. Okay. Same thing if you fly in an airplane. Have you guys flown in an airplane? Who's flown in an airplane? Flown in an airplane. Perfect. Okay. So this is sea level, and here's my airplane up above here. When we're measuring what's called the altitude, okay, you guys get up in the air, and then the pilot comes on and he says, we are now cruising at 35,000 feet or 36,000 feet or whatever it is, right? Yeah. He is measuring from the plane straight down to sea level at a 90-degree angle, okay? You're not going to measure like this distance here at an angle. Like that would be stupid, right? You would measure straight down to sea level at a perpendicular, okay? So that's what we're going to do. Keep that in mind. You are measuring perpendicular to sea level or perpendicular to your other line. We're making perpendicular lines, perpendiculars, okay? All right, let's go to the first example. Here we go, all right? We have 2 points right here that are making a line. They say line L contains points 1, 2, and 5, 4. They've made a line with it. And then we have this other point, which is 1, 7. So if you turn your head slightly, imagine that this is my sea level and here's my airplane, right? And what I want to do is I want to measure him straight down. Now, a lot of times I get this crap going on.
No,
because they're like, well, that's straight down. Well, yeah, but your line is not straight. Like, it's not horizontal. So do you see why that is incorrect? If I want to go straight down, I've got to go like this way so that he's a 90-degree angle. Does that make sense? Okay, so what we're wanting to do is we're wanting to find the distance of this guy. Now, we got to be really particular. Because before we can find the distance, we've got to figure out where is this point right here, where does he touch, right? If I can find out where he touches, like whatever, comma, whatever, then I could just do the distance formula with this guy and this guy, right? I just want to be able to do the distance formula, okay?
3, 3, 3.
So here's what we're going to do. You ready? We are going to look at this guy, and that's my first line that I start with. Let's figure out what the slope is from here to here. Okay, what's the M value of that guy? How much are we going up and how much are we going over? What's the slope? Over 2, up 4, or I think it was Brian maybe, who said 1 over 2. Yeah, Brian said 1 over 2. So that's my slope, right? Now, here's the deal. If this guy is perpendicular, right? What's perpendicular to 1 over 2? What does this slope have to be?
2, or -2.
-2 over 1, or just -2, right? His slope would have to be -2. All right, so let's figure out. I'm going to erase that line. If from this dot I have a -2 slope, that means down 2 and over 1, right? And down 2 and over 1. Oh, look there. He's going to intersect exactly perfect at this spot, which somebody said.
Oh, yeah.
Oh, yeah. Oh, yeah. Somebody said 3, 3, right? Okay. Do you see how that works? We did the perpendicular distance to figure out where he intersects. So now I want to find the length of this little yellow line. I want to find the altitude. Like, how high are we up in the air? If this is my airplane and this is sea level, how high are we up in the air, right? What do I do now? The distance formula between 1, 7 and 3, 3, right? From 1, 7 to 3, 3. This is my distance formula, right? A squared, B squared, C squared. So we take the square root, right? How far is 1 and 3? 2. How far is 7 and 3? 4. I'm listening to you back over there, you whisper girls. I got you. You're doing it right. 2 squared is 4. 4 squared is 16. So this is the square root of 20, which is, if you do it as a decimal, and we got a calculator, what's the square root of 20? I think it's like 4.5 maybe or something like that. I don't know.
I'm trying to.
Square root of 20.
4.5.
4.5 rounded. So it's 4.5 feet or 4.5 units or whatever, right? Got it? That's the distance that that dot is to like the ground, right? So airplane to sea level or whatever it is that we're measuring. Got it? That's how we do that. The distance from a point to a line. All right, moving on. Let's go. They do this really awkward, weird, and we're not going to follow all those steps because that was a lot. And we do it easier. So, example 2, solving this. Okay, I'm going to read this paragraph and we're going to see what it is we're talking about. So we've got our 2 points. Do you see our 2 points in our main street right here? This guy connected to this guy. There's our main street. So we've got a line going this way. And then we've got this point right here. Okay? All right, there's some background information that they give to us. It says the developers of an amusement park want to build a new attraction. According to park regulations, the entrance to each attraction must be at least 10 yards from the center of Main Street. I don't know if they think that, like, if somebody flies off this roller coaster, they want it 10 yards away so that we don't land on Main Street. I don't know if that's their regulation for that. I don't know why. Or if it's more so like they want you to walk through the whole attraction before you get to the, you know, you put all the big rides at the back, so you have to walk through and people get distracted on their way, right? So you don't have just like, you don't put your biggest ride at the entrance of the dang park, because then you're just gonna have a huge line going there, right? So you put it all the way to the back, so everybody has to walk to the back, and then some people get distracted on their way, you know, right? It's like why they put like putting milk in the back of a grocery store. Yes, have you heard that? Like all the milk goes in the back freezers because you want to walk all the way through the store. You have to buy milk like every couple days, right? Okay, so if you go to the grocery store, chances are milk is on your list, right? You have to walk all the way to the back, but you have to walk all the way through all the other groceries, and then you end up finding like 7 more things that you don't need, right? Right? That's a strategy, okay? So I don't know what the rationale for this is, but they want it to be at least 10 yards. So I'm going to circle that. At least 10 yards away, okay? So we need to figure out, is this at least 10 yards away? So I'm going to draw my line. Here, I'm going to make it thicker. Let me undo that. Let me make it this thicker. From there to there, that's my line. Let's make that smaller. From here to here. There you go. There's my line, okay? And I want to draw a line that's from here to the main street, but I'm not going to draw it here, and I'm not going to draw it there, and I'm going to draw it straight so that he's in a 90-degree angle. Do you see that? I want him perfectly perpendicular so that he's in a 90-degree angle. So let's do, what do we do first? The slope. Let's find the slope of the original guy. Okay? And you can count if you want to, but since they're so far apart, let's just do the formula for slope. So -9 minus 3, you know what I'm doing? Okay? 11 minus a -1. Whoop. 11 minus a -1, so 11 plus 1. So -9 minus 3 is -12 over +12. So the slope there is, hey, -1. Okay? So if this guy's going to be perpendicular, his slope has to be +1. +1, right? If you take 1, this is like 1 over 1, and you flip it, it's still going to be 1 over 1, but it's going to be +1. Okay? So I'm going to erase my line here. And let's make him up 1 over 1. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And he's going to touch at that dot, which is at where? 3 -1, I believe it. There he is. Okay, so now what? We want the distance between this guy and this guy. So from -6, -10 to 3, -1. All right, I'm going to do that over here. Distance formula, this guy squared plus this guy squared. How far apart is -6 and 3? -6 and +3. 9. How far apart is -10 and -1? Also 9. You betcha. 9 squared is 81. 9 squared is 81. 81 plus 81 is 162. Whatever that is. Do you know what number that is approximately?
About
12 squared is 144, 13 squared is 169, so about 13, 12 point something. 12.8, 12.7? Is it 12.7? 12.7, okay, now, what were they asking? If each unit represents 1 yard, will the new attraction comply with park regulations? What was our regulation?
at least 10.
At least 10, yes. It complies. You know what comply means? Complies. That's the plural. With park regs. Park regs. It complies. I think that's how you spell complies. C-O-M-P-L-Y-S. Maybe it's L-Y-S.
It's good.
Whatever. Anyway, complies. Good? Happy with that? There we go. That's not too bad. Okay, now, those two are not so bad. This next one's going to be a little bit of a doozy. Just a little bit. And I think out of your whole homework assignment, maybe there's only one of these. One of these that are kind of a doozy. Okay, so here we go. We're doing the distance between parallel lines. Okay? Distance between parallel lines. We've got this going on here. And if we have parallel lines that are like this, it's easy to see that this is like a ladder and this is going to be my distance. So I'm going to try to find the distance between that, right? But sometimes, if you have, I'm going to erase this. Sometimes if you have lines that are slanted, I have kids that are tempted to do this. They're like, the distance is this distance because it's straight up and down, right? Like this is the distance between the parallel lines. When actually they should go this way, right? At a 90-degree angle, perpendicular to the two lines. This is the distance we're wanting to measure, not this guy. Like straight up and down like this. This is not going to be the distance between the two lines. You see that? It's got to be like perpendicular to the other guys. All right. I don't know, because I have people do it all the time. Like on a coordinate plane. On a coordinate plane, if I have this going on here, they want to be able to count and they'll go 1, 2, 3. It's 3 units. Right? Nope, you got to turn it. So it's not going to be 3. It's going to be like something that's really ugly, like 2.6 or something like that. Really ugly. Okay? All right, here we go. We need to graph this baby, and we're going to graph him over here, I think. Maybe-ish. Okay? All right, I'm going to put him over here.
Well, we have to graph on homework.
You might. I'll give you some graph paper. You might have to graph him just to get an idea of like where he's located and stuff. So, it says, find the distance between the parallel lines that are this guy and this guy. How do I know, real quick, that they are parallel lines?
Same slope.
They're going to have the same slope, right? -3 and -3. Okay, I'm going to graph those two little guys. Just do a little rough sketch. One of them we start at -5. So I'm going to go 1, 2, 3, 4, 5. And from there, I go up 3 over 1. Okay, so first line goes like, nope, wrong. He's -3, so I go down 3 over 1. There we go. That's my first line. Let me do that again. That's my first line. Okay? The second one we start at 6. Is it positive 6? 1, 2, 3, 4, 5, 6, and I'm gonna go down 3 over 1. So there's my first dot. Oop. And down 3 over 1, and he looks like this. Something like that. I don't know, mine don't look terribly parallel, but we'll pretend that they are. Okay, like that? Got it? All right, now I want to draw two lines, or like a line that connects him. So I can draw my lines anywhere across here, right? To look like a ladder. But there's two really nice places that I would draw him. I would either draw him from here over, where he's touching the 6, or I would draw him from here over, where he's touching the -5, right? You see that? I would either pick this guy or this guy, where he's touching really nicely. Because what I want to do is I want to find the distance. So I have to know what one of these points is. So let's pick this bottom guy down here. It doesn't matter. And let's say this guy right here is at 0, -5. I have to figure out where this dot is. You see that? I have to figure out where this dot is. Okay, now we don't know what it is. We're gonna figure it out here in a second. This guy is y equals -3x minus 5. This guy is y equals -3x plus 6. Okay? Now the problem is, and the way that this is, the reason why this is different than what we did before is if I have so these guys' slopes is -3, right? The perpendicular slope would be up 1 over 3, right? He's not going to touch perfectly at that spot. Does that make sense? Where he intersects? He's not going to intersect in a nice spot. He's going to go up 1 over 1, 2, 3, up 1 over 1, 2, 3, and he's going to like not be at a good place, right? But I have to figure out where this guy intersects, okay? So let's do this. Let's figure out the equation of this line right here. We know that he's perpendicular, so he's y equals, what will his slope be? 1/3, right? And what's his y-intercept? What's the b value for him? -5. He's touching at -5 right here, right? Okay, so that guy's equation is y equals 1/3 x minus 5. Now, can I use those equations somehow to figure out where this point is where they touch each other? Like this line right here, this orange one, is this guy right here, and he is 1/3 x minus 5. And this purple one is -3x plus 6. Can I do something to those two equations to figure out where they meet? Where they intersect, where they cross each other? Yeah, kind of. Yeah. Do you guys remember doing substitution and elimination? Yeah. To find out where those points cross, right? You remember doing substitution and elimination? So I'm going to write them over here. Okay, let's put the points over here in this little region so we have some room. And let's see, the purple line, was it purple or pink? Purple line. The purple line was y equals -3x plus 6, right? That's the first line that we want to cross. The other one is y equals 1/3 x minus 5. Okay, now, do you want to substitute or eliminate? You want to eliminate? Would you like to eliminate x or y? You want to eliminate x? I don't care.
Why?
Let's do x. Sure, let's do x because I don't want to deal with fractions. So let's do this. Okay. This one's -3 and this one's 1/3. Now, if I multiply this guy by 3, it will make him 1. So what do I have to multiply him by in order for him to become -3? 9. Do you see that? If I multiply this bottom equation by 9, 9 times 1/3 will make 3. Does that make sense? Okay, so he now is going to stay y equals -3x plus 6. And the bottom one is going to become 9y equals 3x minus 45. Do you see that? Yuck. That's kind of gross. The x's cancel. All right, how many y's do you have? 10y equals +6 and -45. -39. Okay, let's divide by 10. Do you know what -39 divided by 10 is? Other than an ugly number with a decimal? Yes, you do. -3.9. That's what he is. Okay. Now, yeah, that wasn't too bad. Now let's plug him in. I'm going to plug him in up here, maybe, right? -3.9 equals -3x plus 6. Can I do that? Okay, what are you going to do first to solve for x? Subtract 6. Okay, what's -3.9 minus 6? -9.9. Okay, and then let's divide by -3. Okay, what's 9.9 divided by 3? 3.3. Is it positive or negative? Positive 3.3. Positive 3.3. Okay, so the coordinate point is 3.3 comma -3.9. That is so disgusting. Yuck. That's really gross. Okay, I'll pause there so you can get that written down, and then we'll move over and see what we have left to do, because there's one more little thing we got to do. Okay, so we have found this place where they cross, which is at 3.3 comma -3.9. Now, what are we trying to do again? What are we trying to do? I'm trying to find the distance. I'm trying to find this distance right here. So, now what? Now I do the distance formula, okay? And I'm going from this point right here to this 3.3 -3.9, okay? So how far apart is 0 and 3.3? 3.3. How far apart is -5 and -3.9? 1.1. Okay, so 3.3 squared. I don't know what that is. 9.89 or something like that. 3.3 squared. 10.89. So this guy right here is 10.89 plus 1.1 squared is like 1.21. If I add those together, I get, I don't know. I get 12.1. And if I take the square root, I get 3.48. That's the distance between these two guys. How disgusting was that?
Never again.
Never again. So because this guy did not come out as a nice point, that was why we had to do that, right? He doesn't come out as a nice clear point when we do the perpendicular slope junk stuff. Okay? Manageable, but please don't give us any of those, right? 3.48, that is the answer. So they say about 3.5 units. Okay? And that's all. Hey, there you go. There's the homework. Very nice. 2 through 10 evens, 13 and 14. Okay? All right. Goodbye, Remington.